I will now talk about how to count what we call permutations and combinations of elements from a set when I do not allow repetition. Repetition, it means you can take the same element from the set more than once. So in this video here, I will not allow that. If I give you a set of letters, for example, A through D, and I say, give me 3 letters from there, you cannot give me A more than once, or B more than once, or C more than once, or D more than once. So this is what we mean by without repetition. In permutations, we care about the order. So if you give me A first, then B, it's different from giving me B first and then A. This is a permutation. In a combination, there is no difference. You are giving it to me as a set. So when you give me A and B, it doesn't matter in what order you gave them to me. Okay, so this is what this is about here. And let's look at the first concept here, permutations. And suppose I have two numbers n and k is smaller than or equal to n. Both of them are non-negative. Then I'm talking about k permutations. How many k permutations are there of a set with n elements? So suppose the set A here is, we have the set A that has 4 elements, A, B, C, D. So the n is 4. And suppose I ask you about a set of all 2 permutations. So what does it mean to have 2 permutations? It means that take any 2 elements from this set, give them back to me in different orders. Okay, so if you give me AB, then you give me BA. These are 2 different 2 permutations. So the different permutations are, you can give me AB as A first then B, or you can give me B then A. You can give me A then C, or C then A. You can give me A then D, or D then A. Or you can give me B then C, or C then B, or B then D, or D then B, or C then D, or D then C. These are all possible 2 permutations. There are 12 of them. The formula that's written on the slide tells me that this number is also the n factorial divided by n minus k factorial. Indeed, this is 4 factorial divided by 4 minus 2, 2 factorial. This is 12, right? 4 factorial is 24, 2 factorial is 2, this is 12. The question is that where did this formula come from? This came actually from the product and division rules. Because suppose, what does it mean to take, for example, 2 permutation AB? How do I get AB? If I look at all permutations that start with AB, so let me look at all permutations of A, B, C, D that start with AB. So this is A, B, C, D. This is A, B, D, C, right? If I want to look at all permutations that start with BA, this is BA, C, D, BA, DC. So if you look at this, you'll find that this here we have the 4 factorial elements. But again, we know that each 2 of them, if I just focus on the first 2 elements, each 2 of them correspond to 2 permutation. So the first 2 correspond to AB, the third and fourth correspond to BA, and so on. The last ones are going to correspond to DC, for example, here. So this is where we use the division rule, that we have 4 factorial possible ways of arranging these 4 letters. The D here is 2. Remember from division rule, the D is 2. So we divide 4 factorial by 2. Okay. In this case, it was 2. In general, we have, when I look at the permutation, I'm asking for the first k here. So the first k, I want to focus on the first k. Then I don't care about the last n minus k factorial ways, right? So this is why the D in this case will be n minus k factorial. And the size of set A is n factorial. By the division rule, we get n factorial divided by n minus k factorial. Okay. Let's see examples of this rule here. In how many orders can the names of 5 presidential candidates be printed on a ballot? Okay, so the set here has 5 presidential candidates, P1, P2, 3, 4, and 5. So n here is 5. And I'm saying how many ways we can order all 5 of them. So really the k is 5 here. okay? So the P of nk is 5 factorial. We have the 5 factorial divided by the n minus k factorial, which is 0 factorial. 0 factorial is 1. So this is 5 factorial here, okay? And this is the number of permutations of the 5 names. It is 5 factorials, okay? So, and when we look at n choose n, or sorry, the number of n permutations from a set with n elements, it is actually n factorial. Let's look at another example here. How many different possibilities are there for the gold, silver, bronze winners in a competition with 10 people? So here the set has 10 competitors, for example, or C1, C2, and C10. I need to choose 3 from them. I need to choose, so n is 10. I need to choose 3 of them. And the order matters, because if you give me C1, C2, C3, then C1 got gold, C2 got silver, C3 got bronze. If you give it to me as C3, C2, C1, then C3 got the gold and C1 got the bronze. So here this is P of 10 choose 3, which is 10 factorial divided by 10 minus 3 factorial, which is 7 factorial. And we usually are not interested really in the final number in these exercises here. What matters is that you figure out how to solve this problem. 10 factorial divided by 7 factorial, it is 8 times 9 times 10, okay? 8 times 9 is 72 times 10, 720. Again, this is not what I'm interested in here. What I'm interested in that you got to this point, okay? Another problem, let's look at another example here. How many different words can be written with the letters A, B, C, all the way to G, such that every letter appears exactly once? In other words, we are asking about the number of permutations of these 2, 4, 6, 7 letters, okay? So here N is 7. The K that I want back from you is 7 as well. I want all 7 letters. This is P7, 7, which is 7 factorial, okay? So there are 7 factorial ways you can write words with these 7 letters that such that each one of them appears exactly once. Another example here is that how many different words can be written with the letters A, B, C, D all the way to G, such that every letter appears exactly once and the word contains D, F, G. So now here let's be careful about it. This is a word that has 7 letters in it. 1, 2, 3, 4, 5, 6, 7. So let's look at DFG. DFG could start from the first letter, so this will be DFG here. Or it could be if DFG is here, then what I have here left 4, there are 4 factorial ways to put the other 4 letters. The other thing could be that the DFG start here in the second, the third, and the fourth, and then we have still 4 positions and we have 4 factorial ways. So DFG could start in the first position, in the second, in the third, in the fourth, and in the fifth. It cannot start in the 6th or 7th. There isn't enough space to put them there. So there are 5 ways, 5 places to put the DFG. Once we put the DFG, that leaves us 4 other letters to put in the other places, and each of them, and for each 4 letters, we have 4 factorial ways of putting them, okay? So the number of different words that have DFG in them and the other 4 letters exactly once is 5 times 4 factorial. And let's look at another example here. How many different words can be written with the letters A, B, C, D, E, F, G, such that every letter appears exactly once and the word contains the string AD and FG? Since we have to have AD and DFG, then what we are saying is that the word has to have ADFG. Okay, so ADFG, it's the same thing as before. This leaves us with 3 other letters, and ADFG could be in the first position, in the second, in the third, in the fourth. There are 4 places we could put ADFG. For each one of them, there are 3 factorial ways to put the other 3 letters. So it is 4 times 3 factorial. And this is, by the way, 4 factorial. Okay? So this is how we count these permutations. When we don't care about order of letters, this is when we talk about combinations. So here I'm giving the same thing n and k, and n is greater than or equal to k. And I'm saying give me a subset of the n elements of size k, a subset of size k of the n elements. But when you give me these k elements, I don't care about the order, okay? I don't care about the order. So notice that the n factorial divided by n minus k factorial, this is the number of ways you can give me k elements where the order matters. So for every k elements, all the k permutations counted differently. Now all these k permutations are going to count exactly the same thing because I don't care about order. So by the division rule, I can divide this by k factorial to get the answer. And this is where I get that formula. The n factorial divided by k factorial times n minus k factorial. Okay, so the number of permutations, number of combinations are really related by the division rule. So Cn choose k is p of n k divided by k factorial. Okay, this is also this notation n choose k in parentheses, n on top, k and at the bottom. This is also a very common notation here. N choose k. It's read as n choose k. It's the number of ways of choosing a subset of size k from a set of size n. And the number of such ways is n factorial divided by k factorial divided by n minus k factorial. Let's look at an example here. How many bit strings of length 12 contain exactly 3 ones? So what are we saying here? We have a string of length 12, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We want to have exactly 3 ones. Exactly 3 ones, basically we are saying, find me the number of 3 positions, the number of ways I can choose 3 positions for the ones here. So I could say, for example, put 1 here and 1 here and 1 here. Now notice that the order doesn't matter. So if this is position 1, 2, 3, 4, 5, this is position 5, 6, 7, 8. So you are telling me one way to put 3 ones is put 1 in position 1, 1 in position 5, 1 in position 8. It doesn't matter if you read it differently. If you said put 1 in position 8, 1 in position 5, 1 in position 1, they are all the same. So this is a problem of 12 choose 3, okay, or C 12 comma 3. It's the same notation. This is just a notation matter. 12 choose 3, it's 12 factorial divided by 3 factorial times 9 factorial. Okay, if I want to simplify this more, 12 factorial divided by 9 factorial is 10 times 11 times 12 divided by 3 factorial here, which is 6. So this will be 10 times 11 times 2. Okay, this will be the answer. Okay, so again, here where you put the 3 ones, it doesn't matter the order in which you put them. They all count towards the same number of bit strings. How many bit strings of length 12 contain at most 3 ones? So now we use the sum rule, because now we are looking at the set A is the number of bit strings with no ones. This is actually, I call it A0. A1 is the bit strings with 1, 1. A2 is the number of bit strings with 2 ones. And A3 is the number of bit strings with 3 ones. And because we need at most 3 ones, it could be 0 ones, 1 1, 2 ones, 3 ones. And of course, the cardinality of A here is the cardinality of A0 and A1 and A2 and A3, because these are independent, they are pairwise disjoint sets. So now a question is that how many bit strings are there with no ones? This is if we want to go by the formula. This is 12 choose 0. And this will be 12 factorial divided by 12 factorial times 0 factorial, which is 1. Indeed, if you count the number of strings that have no ones in them, there's only one string, which is all zeros. The second one is 12 choose 1, then 12 choose 2, and then 12 choose 3. So this number here is really 12 choose 0 plus 12 choose 1 plus 12 choose 2 plus 12 choose 3. You can evaluate them using the formula, but this here is sufficient like this. How many bit strings of length 12 contain at least 3 ones? At least 3 ones. So one way to do this is by saying at least 3 ones. It means that it has 3 ones or 4 ones all the way to 12 ones, right? So how many have at least exactly 3 ones? It's 12, choose 3, or 12, choose 4, all the way 12, choose 12. And we can take the sum of these. Okay, so this will be the number here, 12, choose 3, plus 12, choose 4, all the way to 12, choose 12. This is one way to solve the problem, and this is correct. Another way to solve the problem is, if it has at least 3 ones, how many are there that have 0 ones? It is 12, choose 0. How many have 1, 1? 12, choose 1. How many have 2 ones? There are 12, choose 2. So now these are the ones we don't like, right? These are the ones that don't have at least 3 ones. So now we can say we want to eliminate these from the set of the total number of all bit strings of length 12. So we have 2 to the 12 string of length 12. There are 2 to the 12 bit strings of length 12. From these, we want to remove all the strings that have either 0 ones or 1 1 or 2 ones. So this will be 12, choose 0, plus 12, choose 1, plus 12, choose 2. So you subtract them and you get this answer. This one and this one here, they should be equal. If you evaluate them, they will be equal, okay? It's just different ways to approach exactly the same counting problem. How many bit strings of length 12 contain an equal number of zeros and ones? It's important to think about it. If you think about it for a few seconds, you'll notice, what does it mean to have equal number of zeros and equal number of ones? It means that it has 6 zeros and 6 ones. So the only thing I need to do is that to find the places for the 6 zeros, because the other 6 places are going to have ones in them. So the number is 12, choose 6 here. Okay, 12, choose 6. Find me the places to put the 6 zeros in them. The rest just put ones in them. So this is 12, choose 6. Find me the places to put zeros. You can say the same thing. Find me the places to put the 6 ones. And that will be 12, choose 6 as well. So just the last word that I want to remind you, something I already said, that the number of permutations and combinations are related by the division rule, where the number of k combinations from a set of size n is the number of k permutations from a set of size n divided by k factorial. And the reason for this, again, is that if I look at this set here as the C n choose k, and this is the P n choose k, here this set, then every k factorial elements from here, every k factorials are going to map to the same element here, because the k factorial, when we go to C, when in P, each one of the k factorials matters. When we go to C, none of these matter. All of them are the same element. So every k factorial elements will map to the same element here. And by the division rule, the cardinality of this set on the left is P n choose k. And the D factor here, how many elements in set A map to the same element in set B, is the k factorial. By the division rule, we get C of n choose k is P of n comma k divided by k factorial.